Alright, in this video I'm going to find the moment of inertia of a solid sphere, which is I equals mr squared, sum of mr squared, or in this case it's going to be the integral of rho dv, that's the mass, times the differential volume element, and the density times the differential volume element, and then we're going to multiply that by r squared, which is going to be r of x comma y comma z, or whatever variables we stick in here. Anyway, the density of a sphere is the mass divided by its volume, which is mass over 4/3 pi r cubed, or 3m over 4 pi r cubed. Now the differential volume element, I'm going to kind of imagine, well, I could draw this bigger. Imagine a bunch of, what are these called? Latitude lines, and they measure basically an angle theta coming down from the top of the sphere. The distance from the center line of that is r sine theta, where theta is this measurement from the North Pole. I'd also say that this distance here, if this was d theta, d theta down here, then this distance here would be r d theta. Now we can also imagine longitude lines coming down, and the angle coming from the center of the sphere measuring another angle, phi. And this distance here would be r d phi, or little r d phi. 3, 2, 1. But up here, a distance around there would be r sine theta d phi. It'd be reduced by the same factor that this thing was. So up here, it's much shorter. You see it goes all the way down to 0 up there. So it'd be r sine 0, or 0 d phi for those, for the length of that line up there. So that means that like the area of this little square here would be dA would be r squared sine theta d theta d phi. R d theta coming around that way. Sorry, I drew them in the wrong direction. But that's r d theta, and then this is r sine theta d phi. And then we're going to have that square go a little bit into the sphere, so it'll be a little cube there with a depth of dr. So we're going to say that dv is r squared sine theta d phi, and then we're just going to multiply that by our little dr. And so that's our differential volume element. And the only thing I'm going to change is that I'm going to make those lowercase r's to represent a variable. Finally, I'm going to think about this r here. How far away is each of these things from the axis? I'm going to make that in something a little bit more formal. R of the axis squared, m r squared axis. And so the final product we're going to have I is a triple integral. I'm going to plug in our density first, 3m over 4 pi, and this is going to be a constant here, capital R cubed. That's a constant, because that's related to the constant density. And then we're going to multiply that by, we'll use this r from the axis, and that r from the axis is this r sine theta, actually lowercase r sine theta, because that r is changing. And then we're going to multiply that, that's squared, r sine, and then we're going to multiply that by our differential volume element, which is r squared sine theta d phi r. So I'm going to divide this out into our constant term, 3m over 4 pi r squared, r cubed, sorry, and then the integral with respect to lowercase r going from 0 to capital R, this going from the center to the outside edge of the sphere. We're going to have r to the fourth dr, and then we're going to have the integral with respect to theta going from the north pole to the south pole. And we're going to have a sine squared times sine, or sine cubed of theta, d theta. And then we're going to have the integral with respect to phi, which goes all the way around this sphere. Phi equals 0 to 2 pi, and that's going to be d phi. The most challenging part of this is the integral of sine cubed. So the hardest part is taking the integral of sine cubed of theta. I replace sine squared with 1 minus cosine squared theta, leaving the sine theta. Then I'm going to use a u substitution, setting u equals cosine theta and du equals negative sine theta d theta. This 1 times sine theta d theta stays out here, integral sine theta d theta. Then the negative cosine squared theta d theta times sine theta d theta becomes negative du. Negative negative becomes positive, and then the cosine squared theta becomes u squared, so we got integral of u squared du. The integral of u squared is u cubed over 3, which becomes cosine cubed theta over 3. Integral of sine is negative cosine, so we're going to take negative cosine theta from 0 to pi is cosine. I just reversed the integral here, so instead of going cosine pi minus cosine 0, I just reversed it. Cosine 0 minus cosine pi plus cosine cubed of pi minus cosine cubed of 0, all that divided by 3. Cosine of 0 is 1, cosine of pi is negative 1, cosine of pi is negative 1, and cubing it gives you negative 1. Cosine of 0 is 1. So we end up with 1 minus negative 1 is 2, plus negative 1 minus 1 is negative 2/3, or 4/3. So now we can finish this as 3m over 4 pi r squared, r cubed, times integral of r to the fourth is r to the fifth over 5. Integral of sine cubed we just discussed was 4/3. And integral of phi from 0 to 2 pi is 2 pi. We can cancel the r cubed with the r to the fifth to get r squared. We can cancel the 4 with the 4, and the 3 with the 3, and the pi with the pi, and we end up with 2/5 mr squared, which is the moment of inertia of a solid sphere. Thank you for watching.